HVAC 360 is brought to you today by Big John's Bucket of Crap. Regardless if you take it, leave it, or give it, it's always handy to have some in reserve when you need it. This is some steaming hot product that has just landed on the shelves at Lefty's Construction Mart. Act now with deep discounts available for bulk purchases. I can smell the savings from here. Can't you? Hey there, welcome back. Matt Nelson here, your host for HVAC 360, helping you be the best in the brightest in the field of HVAC. Each week, I'm either sharing information and lessons learned from the field or talking with industry experts, but I don't stop there. I want to encourage you to double down on that weekly helping of HVAC knowledge by hopping on over to HVAC360.com and joining the growing community of people just like you. And I've mentioned this before in the past podcasts, we're doing an added bonus. We're starting a free webinar series in 2019, coming up here probably on the end of the month, actually it is the end of the month if you're listening to this real time, so it's going to be in April. It's probably going to be the first one that's going to come out, and if you want one of those 100 spots available for each webinar, it's going to be on a first come, first served basis, but if you're on the list, then you're going to get notified a couple weeks ahead of time. So, what is up for this week? This week, I wanted to continue sharing about electrical. Before I start that, though, I wanted to kind of take a step back. I've actually got some pretty good feedback from the airflow monitoring stations. And I guess one of the things that kind of surprised me, and, you know, when I do these things and I get the write-ups and I do the research, one of the things that kind of escaped me, and it was brought to my attention, is that I didn't necessarily, I told you what scenarios that I found these things, the airflow monitoring stations, when they didn't work, but I didn't find really some great examples of when they do work. And I'm going to get some research done for you on that and kind of post it as an update on a future podcast. So don't worry about that. It's always, I always have the thought that it's not, typically you have great products, but they're somehow misapplied or applied, the field conditions where they get applied sometimes, really puts them in a bind on where they can actually operate to their fullest. So I don't want to say that some of these airflow monitoring stations are really, really good, and it's just the execution sometimes that kind of falls short a little bit. So I want to be able to kind of give you some positive notes, some actionable items as to where they can be used. So that's going to be in a future episode. This one, I'm going to talk about electricity. I'm going to be talking about electrical, kind of leave off where I did. We talked last week, we talked about phases, voltages, and hertz, and I wanted to kind of dive into some terms and some acronyms. These typically are simple things that you'd find in a equipment schedule or on a nameplate. I want to caution you again that I might misspeak. There might be some information that I'm not putting forward on this episode. So please feel free to correct me. Feel free to reach out to me and correct me, since I'm not an electrical engineer. I've just been in the industry and I know some of these things, and I wanted to share them. And I think that's important. But regardless, I think someone has to start the conversation. So I guess it's going to be me. The most important thing is why do this? This is an HVAC podcast. Why do you keep diving into electrical? Well, I mean, whether we like it or not, we're tied to electrical. Electrical is what makes our motors and our equipment work. So it's critical that you need to be able to effectively communicate with your electrical engineering counterparts and know not only why or what the slew of acronyms mean, but what they really mean. It's words versus meaning. Anybody can know what an acronym means, but what does it actually relate to? And secondly, I think it's important to specify when you're specifying the equipment for the right and correct environment and loads. Last week we talked a lot about phases, we talked about voltages, but you notice we really didn't talk about amps at all. When you think of amps, think current draw. And again, at a particular voltage. The voltage is a differential. So these are some of the things that you're going to see in the schedules. And the terms we're talking about today relate to wire sizing, breaker, and or fuse sizing, so that the system and its users can be safe. I think that's kind of the critical importance here. That circuits aren't being overloaded. And what happens when a circuit's overloaded? It tends to build up heat. Heat leads to fire, and fire is bad. Remember, fire bad. So it's just really a safety thing. The sizing of these electrical components is prescriptive. It's one of those things that, as mechanical engineers, we can kind of get behind because it's very prescriptive. It's in the National Electric Code. At least here in the U.S. and there's a Canadian Electric Code. For the U.S., it's going to be the National Electric Code. They're probably going to be very, very similar. I'm not an expert on either, but I'm betting that they're very, very close. So here is, in the U.S., the National Electric Code, or the NEC. There's another acronym for you. The NEC is part of the National Fire Protection Association standards. That's NFPA. So it is NFPA number 70 is going to be the National Electric Code. So in that group of standards, 70 sticks out. I think some of you probably are more familiar with, I think it's NFPA 90 is more of the mechanical code, or some of the mechanical components to that. But NFPA 70 is the National Electrical Code. So not to say that you really can't use, and again, because it's prescriptive, I don't want to say that you can't use your professional judgment and have a little bit more of a safety factor based on your experience. You certainly can. It's just the NFPA says, okay, here's the minimum. Just like code, it's a code minimum. You can exceed code if you want to. It's up to you and your professional judgment based on your experience. All right, so let's get into some of the terms. I guess one of the terms that we're going to be talking about today that is all over the board, you're going to see it pretty much everywhere, and that is FLA, which stands for full load amps. Now, this is the amount of continuous current that a running motor, remembering it's running, not starting, and that's a critical component. When it's running at its maximum load, so it's and what it will consume. So FLA, full load amps. And why is that important? Full load amps is one of the things that they use, electrical engineers use to size conductors, equipment, pretty much everything. So FLA, that's kind of a standard building block that they use. Now, here's where it gets a little bit confusing. There's two others that are similar in sound and kind of they look similar, and these are all talking about amps, so it's kind of confusing if you haven't gone through it. So we've talked about FLA. Now we're going to talk about LRA, or locked rotor amps. This is used to gauge the amount of starting current of a motor that can be up to 8 times the full load amps. This is often used by electrical engineers to calculate the maximum voltage drop during motor starting. Now, this is critical. We talked about full load amps. That's for when it's already running. But when it goes from a dead stop to running, it's going to draw a lot more current, and that's that starting current that the locked rotor amps is going to be referring to. Now, this really isn't seen a lot. You're going to hear it from time to time, but it isn't seen a lot because it's not often talked about unless you're dealing with a specific motor type. Think fire pumps or other listed motors. So practically speaking, your voltage drop, if your voltage drop is more than 80 to 85%, your motor may refuse to start. and then heat's going to build up. So obviously, locked rotor amps, the rotor is, you're starting from a dead stop, but if your voltage drops more than 80 to 85%, it's just going to sit there and it's going to vibrate like it would be if we're for a single phase motor. It's just not going to go anywhere. It's not going to start turning. It doesn't have enough voltage drop to get it to start rotating around rotate the rotor around. So that's one thing that you just want to keep in mind. A lot of times when you're dealing with the code and the NEC, again, the voltage drop is already calculated. I mean, we talked last week about having like 5%, 10% maximum on your voltage drop. So this is when you're dealing with, again, specific types of motors. You're really rarely going to run into that 80, 85%, but you could for an unknown reason. And now you kind of know that, hey, maybe that's something that I should be looking for. Now, another one that is kind of, they just mix up the letters. Here's RLA. Now, so you have FLA, LRA, and RLA. Now, RLA has more to do with the FLA than LRA. Okay, now I've just totally confused you. Again, full load amps, FLA, that's your kind of meat and potatoes. LRA, your locked rotor amps, not going to find it too much. But the RLA, the rated load amperage, now this is a mathematical calculation used to get Underwriter's Laboratory, UL, approval for certain compressor motors. Now, notice compressor motors. So anything that deals with refrigeration and has compressors in it is probably going to have a RLA and not an FLA, because those two things they're kind of trying to measure the same thing, but they're not interchangeable. You cannot interchange these. The rated load amps is a mathematical calculation. They've been doing that since 1972. And it's critical that you don't confuse it with FLA. Those two things are totally separate. But again, you have all these three-letter acronyms, and you're like, what is the difference? So I'm just trying to help you out, figure out exactly what the difference is, or what that would be for these different abbreviations and acronyms. All right, so now comes a very important. Pay attention. Now we have the MCA, which is the minimum circuit ampacity. Now this is what electrical engineers use to size conductors. Wire, that's a conductor's wire, same thing. But, again, using the right terminology, sizing conductors to prevent overheating under normal conditions. Again, overheating is bad. That leads to fire. Now, the size can be increased when you have the, you're using your experience and you're like, okay, you want to counteract voltage drop, but the size is never smaller than what they specify for that circuit ampacity. So that minimum circuit ampacity, that sets the size for the conductor. So that's you'll see that, and we'll kind of explain where you're going to see each one of these. Now you have, just to confuse things, you have an MCC. Now this is a maximum continuous current. MCC is the same thing used in different situations. That's the same thing as the MCA, the minimum circuit ampacity. This may be confused also because MCC, if you've been around the block as long as I have, you would think that, that's the motor control center for large loads. For large loads, you might have a motor control center that handles, a bunch of air handler fans or a bunch of, large pumps. You can have a motor control center that is dedicated for large loads, and that is also called an MCC, so to make things difficult. So I would not use MCC in your daily goings on. Use MCA. That's going to be very clear. Now, I guess here's where all these things, these 4 different things, play together. So full load amps, the FLA, is generally used for a single motor. That's when you're going to have, that's all you're gonna need. You can calculate your MCA based on that FLA, and you'll be great. But there is situations where you have an MCA that they do that because when you get an MCA, it's usually reserved for package equipment. So think you have multiple fans, compressors, motors, different things adding into the electrical requirement for a piece of equipment, say like a rooftop unit. That is going to have, it's going to have rated load amps because it has a compressor. It's going to have full load amps because it has fans. So you're going to have all the mix of these different loads. And when the manufacturer gives you an MCA, that's typically where you'd see it. So if you're having package equipment, you're going to get an MCA. If you have a single motor, it's probably going to be an FLA. So the one thing that is noted, because you can calculate these things, the FLA is typically 80%, or I should say 80% of the MCA will give you the FLA. So in other words, what that means basically is the conductor wants to be loaded only 80% of the circuit ampacity. And usually you'll see a lot of these. There'll be, these loadings, there'll be different percentages of loadings for electrical equipment, electrical switchgear, all the electrical. You don't want to take a piece of electrical equipment and take it all the way up to its nameplate. You want to back it down 80%. Why? Because that's really the only way that you can allow for one more circuit, a little bit extra. These different changes that happen in all buildings. So you want to give that extra space. So what code says is, hey, just take it down, 80%, and you should be good. Now the MCA, on the other hand, is 1.25 times the sum of all the loads of a piece of equipment. So technically, you could calculate it out if you took the nameplate off of a air handling unit, or a package rooftop rather, and calculated all the different components in there, multiply it by 1.25, and you'd get the MCA. You could actually do that, but typically you're going to rely on the manufacturer, unless you want to double check that, and that's going to be more up to the electrical engineer than anybody else. So you can do that. Now the last piece is another calculation, and this is the MOCP. This is the maximum overcurrent protection. Now, you're probably thinking, Matt, that's only 3 words, maximum overcurrent protection, MOCP. You can refer it to as the MOP. That's also another acronym that's used. So the MOP and the MOCP are the same thing. I guess if you want to split overcurrent into 2 words, then it's MOCP. But most of the time, you're going to have the MOCP, the current protection of a device. This is a number that's used to size the circuit breaker or fuse that is usually specified by the manufacturer. Again, you can calculate your own MOCP, but you can also rely on the manufacturer. MOCP will always exceed the MCA. Obviously, you're not going to have a load that's going to be greater than your circuit breaker. So again, MOCP is going to be larger than MCA or the FLA, but you typically don't see an MOCP in a single motor type of configuration. It's mostly for packages. You see that a lot for or chillers, things like that. That'll have an MOCP, something that's going to be typically larger. It's going to be more expensive. That's when they're going to give you the MOCP. And I have heard that really the manufacturer, if the manufacturer states that a maximum fuse rating is to be, and they list a maximum fuse rating when they talk about the MOCP, that the connection must use a fuse. Now, we'll get into that probably a little bit more, and I have one more installment, and that's really talking about electrical connections to equipment and what those different things are. That's going to be another podcast, but suffice it to say that both the MCA and the MOCP can be calculated or given, so you could double check whatever. So, thinking about schedules. Now we have things that we typically see on schedules, and we coordinate with electrical engineers. You coordinate, obviously, quantity. That's important. You coordinate voltage to make sure it's in the right system. You coordinate phases. How many phases are you going to have? So those two things typically are listed together, whether you're going to have 483 phase, whether you're going to have 2083 phase, whether you're going to have 277 single phase. Again, it depends on what type of environment, what type of system that you're using that in. Then you're going to have an FLA listed for single motors, fans, things like that, or you're going to have an MCA for a packaged piece of equipment. And then you're going to list an MOCP when that is listed. So those are some of the things that you should think about when thinking about schedules, when thinking about coordination. And the last component that we're going to talk about in a future podcast is going to be what those connections are. So, all right. That's it for this week. Thanks so much for listening. I hope this was helpful. Again, if you know anybody who's looking for more information about this topic, consider passing this episode along. We do very well with word of mouth. There's been more and more people finding the podcast, and the best way to do it is kind of sharing it. So I encourage you to let people know about HVAC 360, help get the word out, help spread. Send in questions, send in comments, Matt at HVAC360.com. I'd love to get those, some feedback on these episodes. If you're not a subscriber, again, consider going over and joining the growing community of people just like you over at HVAC360 for more weekly goodness. And always, I would love and be greatly honored if you'd consider leaving me a rating and review on Apple Podcasts. That just, again, that helps, another avenue that helps people understand and find this podcast. All right, well, that's a wrap for this episode of HVAC 360. I'm Matt Nelson, helping you be the best and the brightest in the field of HVAC. And as always, know what you build and share what you know.